Ladies and gentlemen, may we begin? Welcome again to the Research Exchange. I'm Paul Wright, the Director of CITRIS. I want to welcome all of our web viewers on the 4 campuses. And also, there's some flyers in the back for the next Research Exchange where John Paul Jacob, who's at the back there, will be speaking. I want to introduce Professor David Culler, who is the Associate Chair of Electrical Engineering and Computer Science at Berkeley. He's been at Berkeley since 1989 and has also done many other exciting things. For example, he was the founding director of the Intel Lab, which began around the year 2000 in Berkeley. And he was founding director of Arch Rock, which is a very successful company in the space that you're going to hear about today. He is a fellow of the National Academy of Engineering. He's an ACM fellow. And in Scientific American, he was listed as one of the top 50 researchers in the United States. His research is on the network of small embedded wireless devices, and in the past he worked on planetary scale internet devices, parallel computing architecture, parallel programming, high performance communication. Today we're going to see a very exciting project that was funded by the California Energy Commission, taking the Cory Hall building that you know next door and working with folks like Scott McNally and others to really instrument that and show a dramatic drop in the energy usage. This is phenomenal work, and it's a great pleasure to introduce David today. Duncan Calloway, the professor in ERG, will be doing the question time. And so for now, welcome, thank you for coming, and let's give David a warm welcome and a round of applause. Thank you.
Thanks, Carl. Now you can run to the rest of those meetings so you don't, if you're not triply booked. So this is going to be a bit of a nuts and bolts talk about some of the life and times of this project we've been engaging on instrumenting Cory Hall, which has become incredibly timely. Dick White's here. I think originally this was his idea about 3 or 4 years ago, and with Chris Piecer, I'm not quite sure why I got stuck actually executing it, but we'll get into various bits of grunge, and really the goal here is to let you know that there's now a fabulous information source that you can build on, and a number of graduate students in all sorts of different parts of campus are already running with it. The key challenge, I think, is actually understanding how buildings work, and especially a building like Cory Hall. Work may be a big word for what it does, but it certainly operates, and it's remarkable how different it is than, say, this building, which was designed yesterday and is coherent. So I want to start this out at the few 100,000-foot level, and then we'll dig down to the millimeter before we're done. So, you know, the big picture here is we're perhaps at the end of the industrial age of cheap, plentiful energy consumed obliviously, and the architecture that went with it. I mean, the grid is a paragon of the industrial age. If you think, you know, the set of things from a body of generators that manage to predict the load and supplies that follow the load, delivered through a phenomenal transmission system, distribution network onto those demands. I think in a talk I gave here a while back, I described this as the most amazing supply chain, the energy supply chain. You know, deliver this precious perishable commodity to millions of users over thousands of miles with no inventory anywhere in the supply chain, and nobody bothers to place an order. And you know, it's an unfathomable engineering problem, which of course gave rise to the rampant innovation of the Industrial Revolution. So that world is beginning to change as we move from those body of hierarchical tier of supplies, a baseline tier with families of dispatchable tiers which could be scheduled ahead of time, to a number of non-dispatchable sources, wind, solar, and others that are governed not just by the demand. The only way that this is all going to make sense is to create the missing fourth element here, which is dispatchable loads. Loads that are aware of energy availability and adapt to that in how they operate. And so one of the many projects that are related to the Cory Hall effort is LOCAL, which says, you know, if you're going to adapt, for starts, you need to be able to communicate, forecast, predict, give information back to the grid of what you're going to consume. and also be able to receive information about availability prediction and so forth. So locale is tackling that piece of the problem, and in some sense, the lower right corner of yours is the subject of action webs, which is really looking at future views of exotic building control modeled after what we do for the air traffic control system and so forth. So that was kind of where I started. If you're going to make a significant difference in this, where do you start? And interestingly, the answer is buildings, which given the high-tech Moore's Law view that many of us come from is kind of an amazing thing, because these operate in sort of the inverse of Moore's Law. But it's where 3/4 of the electricity goes, half of the footprint. It continues to grow faster. It's where the nastiest supplies are used. It's also the primary place where you could apply renewables. And so that's kind of driving a lot of this, is how do we begin to utilize that particular body of load to become the thing that makes the grid a greener place. So you might ask, what about our buildings? So this is a picture of the energy consumption, electricity consumption of buildings on the Berkeley campus. The national average is about 15 kilowatt hours per year per square foot. And on campus, so you can see that here in the bottom axis is that notion of energy density. And on the other axis is total energy consumed in the course of a year. On average, a campus is about average. And you can also see that things do go up and to the right, but that's not a good thing. What that suggests is that there really is no economy of scale, that big buildings are not more efficient, newer buildings are not more efficient. Stanley Hall, great example. Higher technology, not more efficient. In fact, Sutarja Dai is not yet on the map here, but a reasonable expectation would be that it would fall about right here, because it's almost the sum of soda and Cory combined, and roughly at the same efficiency. Part of this that you need to understand, as soon as people talk about buildings, they think it's all about HVAC and it's about a better air conditioning system, and that's a significant piece of it. That's the environmental part, keeping occupants happy. But if you look at where the heavy users are, and the top 10% account for 70% of the spend on campus, there's significant operational demands. And in fact, here on campus, we're a microcosm of the larger problem, because operationally, we have things that look like IT-intensive data centers, we have semiconductor manufacturing, we have biotech. This is a sort of interesting one. So that many of the problems in the larger world are actually represented here. So this notion of campus as a living laboratory is a very powerful thing. So great. World's greatest information technology, world's biggest problem. Let's put these two things together. What does it look like? So in this case, I have Soda Hall. I'll give you Cory in a minute. And this amazing fact, when you look at it, that there's almost nothing in the signal. If you look at this, is looking at electric power consumption over time for a week. And this is actually during a shutdown period, that we consume 90% of the peak power when we're doing essentially nothing. Great big light bulb. If you look at Cory Hall, it's the same thing, only twice as large. So if we're going to make significant reductions or significant adaptations, we have to understand where that energy spends. This is observing that buildings are far from power proportional. So if you define the goodness criteria of the energy I spend should be equal to or proportional to the work I accomplish. Well, we spend 80% of our energy when we're accomplishing essentially nothing. So there's likely to be a tremendous amount of waste in there, and in fact, that's true. It's pretty predictable, so we ought to be able to anticipate it and adapt. And the real question here that this Cory Hall Building-to-Grid Testbed was really getting at is how much of that load could become sculptable so we could adjust it to become a better citizen on the grid. For soda, the rough breakdown looks like this in terms of lighting, HVAC, IT, and plug load. That's an incredibly crude breakdown from what you get from inventories and whatnot. And what we really wanted to do was to automate this process to be able to dig in and really understand in real time for each kind of resource where the energy spend went. It's also interesting, this mix of what determines that spend. In some sense, that little piece in the middle is determined by the design of the building. Really, the bulk of the spend is determined by how we chose to use that, of course, governed by that underlying design. And the last point here is we have the ability now to essentially instrument anything. So this was a piece of work out of Fred Jiang's PhD, essentially developing high-quality meters all the way down to the receptacle level and taking a lab of 25 or 30 people and really breaking it down to exactly where does any energy go within that group, all the way down to monitors and projectors and refrigerators and so forth. So we have the ability to bring the information all the way down to the physical world if it's not too difficult. So enter the Cory Hall Building-to-Grid Testbed. In some sense, that's the picture of Cory. Oh my God, from the grid's point of view, this is the simplest thing in the world. It sits there consuming a megawatt, day in and day out, right? But in fact, it's this incredibly complex engine underneath between microfab, data centers, and now that we're at the other side of it, I now understand why it was so hard, because there are 16 different independent HVAC systems inside that building, all interacting in all sorts of unknown ways. So the idea here was pervasive monitoring of large complex load with the purpose of understanding the energy spend, how to reduce it, how to forecast it, and ultimately, how do we begin to optimize that in concert with an intelligent grid. So that's really the goal, and this is really the starting point. What I'm going to show you today, and we'll split between some slides and some live demos of things that you can go and play with. We're now at the point that we've got all that information, and the most exciting parts are ahead. The reason this problem is interesting, and the thing that took a year or more for me to understand and I'd like to have in your head, the challenge in building scale monitoring is not measuring the electricity. And it's not getting a hold of the SCADA data for all the HVAC system, and it's not putting occupancy sensors into the room and turning the lights on. The problem is associating that relationship. Okay? It's really these three views. So of course, in this project, what we've done is to take the electric load tree and instrument it well so that we could understand the spend. But the spend is what? It's this cooling plant that stretches throughout the building that provides an environment for the occupants and the operational processes that are inside. So yes, there's a variety of really old-fashioned technology and various kinds of current transformers and so forth, and fabulous work going on here where these could be stick-on and the cost of doing those could be much less. But the point is that every one of those endpoints connects into points in this plant. And of course, we have wonderful sensors for those too, temperature, vibration, airflow. What's really important, though, is to understand their relationship and how they go together to yield a particular function. And I'll come back to this as we start doing some of the show and tell. So the way we tackled this problem essentially was to view this like an audit, start at the highest level, where's the spend, and then dig in, break it up into pieces, take the biggest piece that you can't explain, break it apart and keep going, apply that recursively. That was a nice formal model. Fact of the matter was, as we dove in, every place we went, there were such operational challenges that opportunity was key. So here's a picture over the life of the project, which started in, we started thinking about roughly a year ago, and in some sense, all the instruments went in about July. So Cory Hall had been a megawatt load for decades. Cory Hall today is a 750 kilowatt load. Now, what's interesting is this is all before we had the real data flowing in. So just the act of going through the process of figuring out how to understand the load in the context of Scott McAnally, who was highly motivated to reduce the load along the way, while simultaneously doing a monitor-based conditioning effort, meant that every place we good, it was hard to do this as a controlled experiment because you find waste. You say, how can I live with that? I have thousands of gallons of hot steam going down in the gutter that should be going back to the plant so that it doesn't have to be heated altogether from scratch again, not to mention wasting that water, and lots like that. There's also opportunities. So this was a point where we had a fire in the micro lab. Wonderful opportunity to not turn on those things that you had been fighting with people that they didn't really need. Oh, yeah, we'll turn that on any day now, any day now. That helped a lot. And I'll show you in a minute that this project was 6 months of CEC money. We don't do research in 6 months like that. And it was clear that the cost of the project was dwarfed by shutting down this entire building. You have to understand, we have instruments in that building that cost millions of dollars that if the power went out for a minute would be lost. It was a very dangerous thing. So the university was planning to shut the building down out here in March. So the whole project ended up being driven around that opportunity at some level, which is kind of interesting for the dive in and go instrument it. So what really happened was he did a tremendous amount of careful planning, what we could over the curtailment, so that in this modest number of a couple of hours, all of the core instrumentation went in, and from then on it becomes a high-tech piece of the internet per se. There's a little bit of issue in there. We're also in the process of moving the microfab lab out. So you'd like to say, well, maybe that's where all the savings is. Well, now we can nail that down and all sorts of other pieces. So let me dive in a little bit. We started, this was the state-of-the-art CAD. And I was busy doing photograph fixing this morning, and I realized I put them in the wrong place. So I was going to show you just a little more of that state-of-the-art CAD that unfortunately I put into this one here. So let me show you that one. It's not just this. We also have state-of-the-art CAD. We have a state-of-the-art wiring plant. We have state-of-the-art safety and circuit protection. You can imagine, so suffice it to say that the electrician received the benefit of some high-quality safety equipment in order to conduct the project. Okay, so what's really going on, and Scott does all of his work inside of Excel, is that in reality what happens inside of Cory Hall is it's several buildings inside a building. There's a piece over 4 floors, 2 halves that are essentially 1950s ventilation and heating, no air conditioning. We have labs in the basement that are self-contained systems. We added a new floor on. We added the micro lab. So there's a whole body of electrical intensive tool load and infrastructure and then support for that. The 5th floor has essentially a high-end office environment in the DOP center of just 10 years old. Another one, there's self-contained labs. Turns out more than a dozen different HVAC systems. And a really unusual power plant down inside. So we take this up a little bit before I walk you through how we did it, that one of the things we have is the ability now to observe all of the pieces down inside. And there's also a piece of technology here that really transcends this project and is, in my view, the biggest basis going forward. So coming at this from an IT part of the world, our world is horizontally stratified. We understand that there's physical layers, there's logical layers. Our networks are built this way, our systems are built this way, and part of that is so that we get the benefit of using innovations in technology with the applications and analyses, new applications on existing technologies. The building world is vertically integrated in everything. Your repository, your portal, your analysis tools are integrated all the way down to the particular wiring of the building. So the most radical thing here in some sense is re-stratifying that whole world into meaningful layers. Going in, all of the emphasis is in here. Are you getting the last harmonic of the power signal? Are you capturing the SCADA versus lawn talk? Whereas what we need to do is elevate that up into what really is a logical layer of what is the data, not the instrument. what is the environment, not the transducer, so that we can raise that up to talk about simulation analysis and control at a higher level, and portals and presentations that are meaningful across that. So I'm going to structure my presentation a little quickly in that same. This was the physical layer. Wide variety of different sensors, not just electric meters, lots of different kinds of them, traditional revenue grade meters, very exotic meters, quite high density, decent quality, little wireless meters all over, thermal ones. Part of what we tried to do is to get the entire energy envelope of the building, not just the electrical coming in, but the steam coming in, the steam coming out, the solar incident radiation, steam, weather, as well as the existing plant, and you see a picture you can't see there. The key in all of this is to map out where does power flow and then how to make sense of it. The story in Cory is a little unusual. So in most buildings, you have, and for example, here on campus, we distribute 12 kilovolts to each building, essentially have a substation, typically break that up into 480 and things that are 240 and 110, things you recognize, which we then distribute through the building at various levels through a body of panels, breakers, subcircuits, and so forth. Part of what you're seeing here is different instruments for monitoring the electrical usage at different levels of that structure. Not too surprising. What actually happens in Cory is that where it arrives, it splits in this god-awful, dangerous closet into a dozen different feeds that are high voltage, three-phase, spread across the building. And right there, that gave us a way to reach in and break the load down into about 10% of the total. 100 kilowatts, we could start to get somewhere. And already at this physical level, we did a radical thing. We said right close to the instrument, conventional instruments, with yucky serial ports and things like that, lock that up, put it on Ethernet, make it a part of the network, and use a VLAN so it's protected. So in Cory, we have now an instrumentation network that goes throughout the building that's built out of the same stuff as all of our data networks, but is completely separate until we glue them together. While we're at that, that means, of course, you're going to move it to interactive web services, so all of these different kind of devices all look the same, and we can start building applications on top of it. So that causes us to work through what is the basic connectivity, what's the low-level data model, Modbus, a bunch of registers, what do those 16-bit values mean, relate them to channels, voltage versus current versus power factor, raise that up. So that was the thinking that was stretching out in that point up to March. And a tremendous amount of work getting all prepared. So I thought I'd give you a little photo. You can see this is our high-end instrumentation network to be of Cory Hall. And here we are filling it in and we now have hundreds of points. And notice the wiring is only going from the current transformer attached to the conductor to some place close where I can put it on the network. And the issue with this lovely opportunity is in Cory Hall, the transformers are so old, they were put in before the skin of the building went on. And they cannot be removed. So every 10 years or so, they have to change all of the toxic oil inside. And it's a thing, you can kind of get a sense of this. It's not where us, computer science folks tend to go. So the moment they shut it down, our team went in. These guys are running literally hundreds of wires over from one side to the other. You can see it here. And, okay, this is an example of a thing called a Rokowski coil. It's a variant of a current transformer that's soft and moldable. It has some different characteristics. These are these high-power conductors that have been in the building for 65 years. And if you were to crack one of those pieces of rubber, we'd probably have to take the building down. So it was a little exciting to get in there and get that project done. This is showing it further along, and you can see a mix of, let's see, just give you a sense that down in there, it's a room about this wide, where every column of it has these dozen or so huge switch with these massive bus bars that are 12,000 volts. Here you can see it a little farther along, and you can see different kinds of transducers for different purposes at different scales. I have to show the pictures. And here you can see, in addition, the P-cube transformers locked onto the bus bars that are feeding 12 kilovolts in from the building, to the point where Dave Shackleton has now all of that horrendous stuff essentially brought into a modern IT infrastructure, that now this becomes effectively part of the real world web. And you can see Dave is really happy. And we got to do that for the microfabrication lab and all of the other parts of the building. I wanted to give you a close-up so you could see the high-tech documentation right there on these circuit breakers, what it is. So throughout the building, these god-awful power panels that are brought into some little teeny device like that makes it part of the network, and we can build it up as meaningful information on top. Then we go about raising it up and homogenizing it just like every other piece of information on the web and in the world. Bring it up to a decent network, get the information to be something you understand without reading the data sheets, despite coming from a zillion different boxes and at different places with different connectivity protocols. And then the next step was essentially to do what we do with XML or other information. We call it SMAP, Simple Measurement and Actuation Profile, that takes all sorts of different kinds of physical information and packages them up in compact, self-describing data structures that you transport around the network. We use JSON rather than XML, partly because we can transcode between the two, but in large part because it's programs, it's software, not people that look at that information directly. And what's really important is that you integrate into software well. So I'm going to show a little bit of that. But more or less the picture we have now in Cory Hall is all sorts of these different traditional devices, all sorts of exotic low-power wireless IP devices and others that either directly or through a proxy speak this SMAP protocol, as do almost anything else in the world. We grab the Cal ISO data. We grab the Weather Underground data. We grab the SCADA data. We grab the Campus Obvious data. We grab almost any data you can imagine, homogenize it together so that you can build interesting applications, and people have. One graduate student built Facebook for Places, Placebook. Go create the building for the bottom up. I mean, I, of course, have my Cory Hall gauge on my, it's 589.7 kilowatts right now. One of the undergrads has built a lovely system where you have some of these devices, or rather those, take your cell phone, walk up to the device, and get its energy profile, or establish your occupancy within the, so innovation on the application side. And I think, and of course it's beautiful because it's just a resource hierarchy, and it's the stuff that people just love to read like this. You know, you go reference that, and it all comes back in a convenient, handy way. So let me show you that, and then we'll flip over a little bit too. So this stuff is so easy to use. Even professors can do it. This was a tool I built out of this, and George Ortiz is in the back. He's been building a much more significant information store for capturing all of this. What you see here is essentially the equivalent of the electrical schedule that would be in your CAD plans. I could go to any particular part of the building, and I can identify what is the box, the panel, the device, the load, and what is its property and what is it connected to. And inside of Cory, we now have hundreds of those. Okay? That's the underlying structure. The other thing we have is zillions now of information feeds of very interesting parts of that. Most of those are in Cory, but some of them are in Soda, and we've now done a deployment up at LBL where there's 100 or so plug level meters up in Building 90. But you see all sorts of other things like the ISO grid demand. We could go take a picture of that and see that the current energy demand in California right now is at about 32 gigawatts. And of course, I can now match up how the use in the building corresponds to the grid. But once I have this picture, then I can construct from that what is the actual load tree. And here, let me close this all. So I said Cory Hall begins with this fan out of a dozen or more, oops, let me go to that, different pieces, different legs. And we now can open that up and we can look at how much of the energy is spent across them. 140 kilowatts going into the HVAC loads in the microlab, for example. 76 kilowatts currently going into lighting. And, of course, we can look at that much more interestingly over time. So here we're seeing for the last 24 hours the load overall in Cory Hall, which we can dig down. And everything I'm showing you here is data you can get to and you can make sense of. And you could go in here and you could adjust this. Let's look at it instead of today. Let's look at it for the last several months. And there you can see daily trends and monthly trends and all the rest of it. And at any point in here, oh, not in this one. We can go hit the button to get the data out. So this is a pretty good tool. And let me expand it out just so you get a picture of it. This is what Scott McNally makes tremendous sense out of. That he's able to walk through this tree of all of these different loads and how they're connected and knows exactly what they are. Oh yeah, here's the lighting in the DOP center right now is consuming a half a kilowatt. But mere mortals like I cannot make any sense out of that. But the nice thing is that once we have not only the source of information, but where it came from, that this information is lighting for the DOP center, and it's got a particular sensor, then we can begin to re-aggregate the information in more useful ways. So here we have the dozen different HVAC systems that are simultaneously operating in Cory Hall. So if we wanted to go take a look at the microfab lab, we can see that it has a mix of hood fans, those are the things that keep graduate students healthy and happy, a chiller, another chiller, and a supply chain to move it forward. So we're spending 100 kilowatts day in and day out on bringing cool stuff in through the microfab lab. And you could say, isn't that amazing? 24 hours, day in, day out. We could look at it over a long time. We must be producing wafers nonstop. We must have graduate students in there nonstop. And that's the story everywhere as you look at waste, is it doesn't matter so much where you look at it. As opposed to, let's go look at the demand of all of the equipment in that lab. So we're spending about 100 kilowatts also in equipment, the vast majority of which, look at this, 70 kilowatts, just day in and day out. Some of this equipment is actually a little bit interesting. Okay, so we now can go in and start answering questions like, how do those things compare to the aggregate plug loads throughout the building? Surely the only thing we need to do is put in some incentive strategy and people will suddenly change the energy profile of the building. No, it has much more to do with where the energy goes. Here's an interesting one. Let's go look at, so we could look, for example, at the collective lighting. Let's go, turns out Cory Hall also feeds the parking lot. So if we were, let me crank this up to look at about 6 months of data in the energy consumption of the parking lot. Aside for one. So we're sitting there spending 23 households worth of electricity day in, day out, month on, month off to light the parking lot with one little spike. Okay, so you get the picture, and part of what I wanted to suggest to you here, let's compare that with what's going on in ventilating the entire core of the building. That's 30 kilowatts versus the quality of the air conditioning system in the DOP center. Look at this. Something that actually shut down from midnight, right? Modern tools. So, and part of what I wanted to suggest, a lot of folks are getting at this data. They can never understand what it means. So this gives you enough of the context. And then you could go and you could grab this data and you could shove it into your Excel or your MATLAB and you could go do some real worthwhile analysis. And I wanted to point that out. Okay. So I'm just going to wrap this up then with a couple of stories and take some questions. So you could do, for example, analysis of if you had to shed a bunch of load, how much of it, of the aggregate, could you shed? We've done that kind of thing. Here's a nice one. In the meantime, we used this. There was monitor-based conditioning going in. We solved the simultaneous and heating problem down on the 3rd floor. And Scott went and noticed, oh my God, on this cold day, the chiller on the roof is still burning 7 kilowatts nonstop. What's going on there? Well, the answer was, when we got all done with that recommissioning, somebody went up on the roof, and even though it was on a schedule, they put the automatic switch into manual. And so we figured that, and now, you know, it behaves like it should. Every now and then the killer kicks on. And Scott, of course, should ask the question, gee, is that still true? So we could go in and we could go look at that particular thing. Let me go find AC 91. Oh, there he is. Let's just go take a look at that and see if that's still operating the way it should. Oh, look at that. Looks like it's still working. Isn't that a nice thing? And, you know, let's go look at that over a little bit of a longer time. Yeah, how about that? It even gets warm lately. This was the summer that wasn't. And this was the summer that we had a little bit too late. Okay, so you can start to make real sense out of what's going on here. So, you know, that was the problem. Now we're happy. We can assess the total cost of the micro lab move, and it's very interesting. You know, we've shed about 40 watts of tools, and what's happened is we're now spending even more cooling relative to the work because we haven't started to shed any of the cooling capacity that's driving it. We found things, I didn't quite get, I guess the estimated was $10,000 of energy lost because this steam condensate was going down the drain rather than being circulated back into the campus steam plant. It's also not a great thing to do in a drought-ridden place. Other students are going in and looking at true versus reactive power and to disambiguate various pieces. You know, you might, for example, be curious. Let's go look at other aspects of the building, like how much do we spend on the elevators? So there's our elevator spend in Cory Hall. It's actually kind of interesting how much energy you spend when elevators are largely standing still, but we can take all of those kind of pieces apart. Other students are looking at how do we use the thermal storage essentially as the equivalent of electrical storage so that by adjusting control strategies we could shift, not just do pre-cooling on a daily basis, but begin to adjust the actual on-cycle and off-cycle of all of those pieces so that when the wind is blowing, for example, we work more aggressively and we shift the fraction of our consumption from conventional dispatchable loads into renewable loads. I indicated that this technology now is moving out to other places. One example is Building 90, where they have about 100 nodes monitoring all sorts of electrical equipment, so we can drive that down. Same SMAP infrastructure to make sense of it all. Students sticking it all the way in your iPhone. What's the consumption? And now really the software infrastructure to start doing the kind of higher levels of what would be a grid responsive building. My lesson, we started this with this very high level picture of a cooperative grid where all the loads are smart and they're interacting. Fact of the matter is, number one, get rid of the waste. Learn to do nothing well and don't waste. Then focus on power proportionality, that the usage of energy should have something to do with what you're actually doing, not continuous. Then you can talk about how do you shave the peaks, move the values, sculpt it, move it around, and then you can talk about when do you consume what you consume. The underlying piece throughout all of that is information into what's going on in the first place. So that's the right place to end this. And I think I'd like to stop here and take questions.
Do you have any questions?
I guess I'm just wondering, how feasible do you think it'd be to implement the same process in other buildings? I guess both in terms of cost and inconveniencing them by having to shut it down possibly, or?
So I don't know of any building that would be as hard, and it's so much easier after the first time. So the piece I walked you through a little bit of building up the electrical schedule, the tree, the systems, oh my God, I wish we had that first. Rather than, after the project has been done for 4 months. Now that I have that view, we understand how to do that, we've got the tools, of course you do that first. So we are doing it for CITRIS dye, and almost no building would be as difficult as Cory was. There's no excuse for not knowing what's going on inside the building. So you don't eliminate the need to actually understand what the electrical plan is and what's the HVAC plan. That takes some work no matter. But capturing that and actually instrumenting it then become much more straightforward. So I'm actually very optimistic. The exercise here is interesting because we are putting in none of the equipment. That it's just the standard stuff that Siemens puts into the buildings. What we're putting is this kind of an information overlay on top of it. So those can happen as well.
So we looked at an older building that you instrumented.
Yeah.
And then you talked about design and use. So
Yeah.
what is the lessons from here for new buildings?
Number one is, why would you ever build a building and put all that stuff in there and not put the information plane in too? It costs next to nothing, and it's so easy when the building is still what you think it's supposed to be. It's so much harder if you wait 70 years and you put a new. So it is just amazing to me that we would build things that cost $100 million and take millions of dollars a year to run, and instrument none of it. We fight over a 15-minute meter for an entire building, which shows you almost nothing other than it's too big, and I wonder, right? So, the lesson here has been fabulous. Being able to get down to a chiller. This thing is as big as this stage. It's hundreds of thousands of dollars. For a few $100s, you can measure it. And then you can say, oh, it's on. It's cold out, and the chiller's on. So, that's the shortest lesson. And the other is break the vertical mold. That Just say no when it's my proprietary slice, because there's so many places where the information is valuable. I think the industry is understanding that. They've understood it for 40 years down here at Modbus and RS-40. And raising that up to where people can actually write the code and do the analysis, it's just so easy to do. No excuse.
So maybe actually following up on that, another question that I have is, so I can imagine how you can get to a point where you can efficiently put in the instrumentation in other buildings and sort of scale that process up. What you described in terms of finding all of these opportunities for energy efficiency was a very manual, labor-intensive, human-intensive process. And what's your sense of the hope for taking the human out of it to get to a point where, yeah, we've got all this information, how do we process it efficiently and find those low-hanging fruit?
Yeah, that's a good one. So I mentioned that a number of projects are getting started doing the analysis of the data. And I have to amuse you because it's late. So, for example, they're doing very sophisticated statistics to pull out the trends. So part of the challenge in general for I want to get you to reduce that energy consumption is, unlike driving your car where you get this very active feedback, you need to look over several months, that you really have to compensate for usage and for weather and various things, right? So the turnaround is very low. So, for example, in some of the statistical analysis, they say, oh, let's pull out the ones that have interesting variations over the day, and I can pull out the daily pattern and so forth. What you actually want to focus on is the things that are statistically uninteresting. They're sitting there, they're a flat line no matter what you do, day in, day out, all the time. So there's even trivial analysis that can say, why don't you go look at this problem, right? Then the piece comes, the problem you talked about, who can make a difference? So you can change the set points in your office a little bit, but that's not going to change the basic control strategy of the HVAC system. So what these tools can get you that first step of, I can make a difference in this piece. So I'm partly suggesting that just throwing a portal where we see the meter going up and down, you actually can't do a lot with that because the instantaneous value or how today looked isn't good enough. What you need to understand is, how is this different from the larger trend for the piece that I have some responsibility for? So when we get down inside of repairing a piece of the cooling system, that's in some sense a professional process and should be. When we're getting at the part of saying, well, why is it that we insist on lighting the building when none of us are here? Well, that's a social choice that we could make. And part of the tool here is that you can get that kind of discussion. Okay?
So one of the questions I'm really curious about is, what are the takeaways from this that come because it's an old, complicated monster of a building, and what are the takeaways from this that come from the aspect that it could be instrumented on this building here?
So for starters, as big and wonderful as this building is, it looks like the simplest of the 14 ones that we did over there. It should be a no-brainer. No excuse. That's one takeaway. So perhaps what that says is that there are natural units of consumption and change. Identify those units. So for a building like CITRIS, the entire building is really one system, and it's very natural to simply capture the mechanics of that, the operational processes, the model, and affect its control function. It's easy, and we should absolutely do it. The reverse is Cory Hall is actually a very nice test bed because you have self-contained buildings within that building. So there is, for example, 199, an instructional lab that has very interesting behavior and essentially is like a little microcosm of a whole CITRIS. So those are tools where we can evolve our technology forward, affecting a small population in a very predictable and understandable way, and advance it. So both have a role.